left off. So no one's going to know that we actually forgot to start the recording, and then I faked that we did the recording here at the beginning, other than it's recording right now so everybody can know. So we're going to start talking about functions. We started by defining what a function is, which is just a set, or started by with the definition of a set, which is a list of mathematical objects where no object repeats. In this class, when we talk about mathematical objects, we're really just talking about numbers, although there's no reason a set couldn't contain other things like triangles or vectors or something else. The notation we use to write down a set, we use a capital letter to name it, and then we use an equal sign, and then one of these curly brackets, and then if our set is finite, we just list the numbers that are in our set. So a finite is a list that ends. This list contains just the four numbers, 1 or 3, 4, 5, and 6. That certainly ends. So we can just list them. If our list doesn't end, we need to use a slightly different notation. So an example of that, if we have the set B, we write B equals, and then I write the curly bracket, and then I write a variable as a placeholder. This variable I'm going to use to describe a rule that describes the sets. And then I'm going to draw this vertical line, and the vertical line just represents the word such that. So this reads like B equals the set of x's such that some rule pertaining to x. In our case, we talked about, say, the numbers that are greater than 3. So the numbers 4, 5, 6, 7, 8. If I have greater than 3, that doesn't include 3. But I should be a little bit more specific than even this, because there's different kinds of numbers. The numbers that I listed, 4, 5, 6, 7, etc., are not the only numbers that are greater than 3, right? What kind of numbers didn't I list when I did that? So we said we're talking about our infinite set that we're trying to write down is 4, 5, 6, 7, 8, etc. And I wrote x is greater than 3, but that doesn't really mean just the numbers 4, 5, 6, 7, etc. That also is including some decimals, right? So we want to make sure that when we write this rule, that we don't mean any decimals. So do you remember the name that we give to the numbers that don't include any decimals? Integers. Wonderful. So the integers are the positive, negative, whole numbers, also including 0. There's a symbol that we use to represent the integers that probably you haven't seen before, but I'll write down here in a second. So we have, again, what we're going to say here, B is the set of x's such that x is greater than 3 and x, and then I'm going to draw this symbol. This little E symbol here, I know I'm throwing a lot of notation at you. Just means is a member of, and then this symbol is the set of integers. So just to kind of reinforce this idea of finite and infinite, if I wanted to write down the set of students in this class, do I need a finite set or infinite set? Finite. If I want to write down the set of weights between 100 pounds and 200 pounds, finite or infinite? Listing all the weights between 100 pounds and 200 pounds. That's infinite. So you could have 100 pounds, right? You could have 100.1 pounds, 100.01 pounds, 100.001 pounds, and you can see really quickly that if I go on like this, I'm never going to finish that list. Does everybody kind of see that? So be a little bit careful. So finite means like you literally can count everything. Infinite means that it might not be countable because there's just, you keep trying to make your list and you can always add something in between. So things that are infinite could be weights, or heights, or lengths, right? Temperature, like the number of degrees between, or the number of temperatures between like 70 degrees and 71 degrees. Does that, everybody kind of see that? As opposed to like the number of leaves on that tree. That's finite. You could count up all the leaves on that tree. There's going to be a lot of them. It's going to take a long time. But it is finite. You guys kind of see the difference? Okay. We feel good about finite and infinite, relatively speaking. Okay. All right. So we talked about what a set is. We've talked about the ways that we can write down to describe a set. What I want to do now is talk about something called a relation. So a relation is a set of ordered pairs. So when I talk about ordered pairs, I mean x, y's, just like we had points in geometry, where the x's are coming from a set D that we call the domain, and the y's come from a set R that we call a range. So, for example, consider the set A. How many ordered pairs does A contain? 3, right? So what kind of set is A? Is it finite or infinite? Finite. Okay. So, if I talk about the set D, what 3 numbers were in the set D? 1, 2, and 3. The x coordinates. And if I talk about the set R, what 3 numbers were in the set R? 1, 2, and 3. In this case, the sets D and R were the same set. Is everybody okay with that? So we could say the domain here is the set D containing the numbers 1, 2, and 3. And we can say the range is the set R, also containing the numbers 1, 2, and 3. Yes, sir.
So are domain and range basically like two words the same thing?
The domain and range may be the same set, but they do not have to be the same set.
Probably like they're both sets.
They're both sets, yes. The domain is a set, the range is a set. Typically, we think of the domain as the beginning, and the range as the end. And to change the domain into the range, we do some mathematics on those members of the domain. But we'll get there when we start talking in more specifics. Just kind of trying to build out some very basic definitions and do a little bit of notation. Because my assumption is that nobody's seen really any of this before. And it is a little bit technical. There's a lot of new vocabulary and new symbols, so I want to go kind of inch our way through, baby stepping through, so that it doesn't go too fast and we don't leave anybody behind here in the first couple of days, okay? So again, if you have clarification questions, please raise your hand and ask them. If you have, I need more example questions, please raise your hand and ask for it. I'm happy to do any of that kind of stuff, okay? Okay, let's do another example of a relation. Let's write a relation that is an infinite set, though. Okay? So, what kind of objects are inside of a relation? They're ordered pairs, right? That's strange. Hope the school's not on fire and nobody told us. So I'll start with the set of xy such that and then I'll write a rule, like y equals 2x. And then I really should say what these x's are. Maybe we'll just say those are integers. So this is an example of an infinite relation. So what this reads, if I read the symbols here in words, I have that the set B is, or I should say B is the set of xy's such that y is equal to 2x and x is an integer. And what do integers mean? Positive and negative whole numbers, right? No decimals. Okay with that idea? But the integers are infinite, I heard somebody say. Yes, there is no limit to the number of integers there are. So can somebody tell me an example of one of the xy's that are a member of B? Yes, sir.
X more than y.
Good, yeah. So the ordered pair 4, 8 is a member of B. Everybody can see that. If I pick x to be 4, and I follow this rule, the y would need to be 2 times 4, or 8. What's another example of an ordered pair in that set? Anyone? Yes. 6 and 12. Very good. That if I pick x to be 6, then y has to be 2 times 6, or 12. Yes. Yes. Good. Can I pick anything I want for x? I can pick anything I want for x as long as it's an integer. Can I pick 5.5? No, because 5.5 is not an integer, because it is a decimal. Everybody's okay with that? Okay. So in this case, the domain is just the integers, right? We're told that in the set, we kind of need to know what the x's are in order to do this, right? What is the range going to be here, though? Which coordinate is the range telling us about? The range is about the y's. Now there's infinitely many of those, right? Yeah. So she asks, why is the domain the integers? And the reason that is we're told in the statement for our set that the x's are coming from the integers. The domain is just the set where the x's come from. We're told in the statement of the set where the x's are coming from. So the domain is just that. Is that okay with that idea? Kind of. No, it's okay to ask and want some more follow-up. That's perfectly fine. Please stop me and ask those kinds of questions if you're not sure. Okay? Don't let a little problem become a big problem. It's much easier to deal with the little ones right here and now. And the reason, let me give a different example or a different way of thinking about this. Let's think here for a second. Let me think. I can't think of a good example of how to do this. I was not prepared for that. But to try to answer your question a second way. So if I read this statement, it says B is the set of x, y's such that we find the y by doing 2 times x, and the x's are coming from the integers, right? Our definition for the domain is where the x's come from. In this problem, we're told the x's come from the integers. So the domain is just the integers. We don't have to think about it at all. We're just told it in the problem, or told in the statement of the set. Does that feel okay? Okay. The range is a little bit trickier, right? If I look at these y coordinates, what do you notice about all of them? They're evens, I heard somebody say, right? They're even numbers. If I do 2 times a number, what am I guaranteed to get? An even number, right? So here is a case where I would just describe this set in words. I would just say that the range here is the even integers. I would not expect that you guys are able to write an infinite set in set notation. Not an expectation for this course. I would expect if I wrote an infinite set in set notation, you could give me examples of things inside that infinite set, but I wouldn't expect you to be able to write an infinite set from nothing. Is that okay there? So like before where we were generating examples, that's an expectation. I would expect you guys to be able to do that. To be able to write this on your own from nothing, I would not expect you guys able to do that. So that's not an expectation for this course. Although you should be able to read it and understand what it says, to generate that all on your own is not something that's realistic for you guys to do. Yes?
So this is that if we were to ask like the label on the set, if we had D is integer,
Mhm.
if we put R is I don't know if we wrote R with 2x is always closing in the beginning, would that be acceptable for that's the range?
So if you wanted to write the range in like an infinite set notation, you would say something like, this is the way you would write the range as an infinite set. I don't need you to be able to do that. You can write it in words in this sort of situation, and that's perfectly acceptable.
But writing 2x would not be acceptable in range. The domain that is
If you just wrote 2x, no. If you had it like inside of a set bracket and maybe a little bit more, I might get a little bit more generous on that. But just 2x by itself, I probably wouldn't take. I might give you some partial for it because I could kind of see that you're thinking the right way. And if you put like the set brackets around it, probably a little bit closer yet, is kind of where how I would be thinking about that. Does that help? So these what-if questions about how I would score something are perfectly fine to ask. I'm happy to answer these things, especially early on in a course. Like understanding my expectations for work is really important, right? And you're more than welcome to ask those kind of what-if questions, and I'll try to do my best to talk about like what I would say is acceptable or what is not acceptable. And when we're doing stuff like this, especially this kind of topic that's rather technical, I'll try to be clear about what sort of things I'd expect you to be able to do and not do. So like writing an infinite set on your own from nothing, I wouldn't expect you to be able to do. Rather, being able to understand what it says and like generate examples from that set, I think is a fair question for you guys. And it seemed to be we didn't have much of a problem with that when I asked for examples earlier, right? 3 or 4 of us had examples right away without too much of a problem. Okay, so we've looked at 2 different kinds of relations, right, which are just set of ordered pairs. We've talked about sets and what those are. They're the building blocks of a relation, right? I take 2 sets and I do somehow match up the things inside of them to create a relation. Everybody agree with that? We're ready now to talk about what a function is. So we say a function is a kind of relation where every member of the domain is paired with exactly one member of the range. So, question, which one is there more of? Do we have more relations or do we have more functions? I'll come back to you just one second. Let me rephrase and ask a different question then. Suppose we're talking about dogs and mammals. Which one is there more of? Dogs or mammals? Mammals. Why? Because dogs are included in the mammals, right? Every dog is a mammal. Everybody agree with that? Let's read this definition of a function again. What does it say? Function is a relation. Just like a dog is a mammal, right? Which one is there more of? Relations. That was the R word you were trying to say. Relations, right? Because every function is already a relation. Everybody okay there? So if we think about it as a picture, if this is the relations, inside of that are the functions. Right? Every function is contained inside of the relations, but there are some relations that are not functions. Is that okay with that idea? This should sound a little bit familiar from geometry last year, right? Just like every square is a parallelogram, but every parallelogram is not a square. There are lots of those relationships when we talked about quadrilaterals that hopefully sound a little bit familiar, even if you don't remember the specific details from last year, which you don't need to for this course. Remember anything about squares or rhombuses or any of those things. Okay? So let's look at an example here of some things that are or not functions. So let's say we have the relation with the ordered pairs 1, 2, 3, 4, 5, 6, and 7, 8. Is this a function? Yes. If I look at the x's, 1, 3, 5, and 7, each of those x's is paired with exactly one y. 1 is paired with exactly 2. 3 is paired with only 4. 5 is paired with only 6. 7 is paired with only 8. Can everybody see that each x has exactly one y to it? What would it look like if it was not a function? Let's take a look at this relation. The relation B contains the ordered pairs 1, 2, 3, 4, 5, 6, and 1, 8. Is this a function? No. What is the issue? Yeah, 1 is paired with 2 different y's. 1 pairs with 2, and 1 pairs with 8. Everybody see that? So, what is our kind of shorthand? What are we looking for if one of these sets of ordered pairs is a function or not? A repeating, which spot needs to repeat? X. Yeah. So this is not a function. And what we're looking for is repeating x's. Does it matter if the y's repeat? No. So let's look at an example where we have some repeated y's. So here let's consider the set 1, 2, 3, 2, 5, 2, and 7, 2. I notice here that x is paired with only one number. It's a 2. That 3 is paired with only one number. It's a 2. 5 is paired with only one number. It's a 2. 7 is paired with only one number. It's a 2. This is a function. Even though the y coordinates repeat, we haven't violated the definition of a function. Everybody okay with that idea? Okay. The reason that this property of the x's can't repeat is so important is because it allows us to be like deterministic about these functions. Imagine if you have a machine that whenever you do, like put a quarter in, one specific thing happens. That would be nice, right? What happens if you put a quarter in and like one of 3 things could happen, but there's no way to predict which one of the 3 things would happen? Not so nice, right? That's essentially what we don't want to happen with our function. If we give it this input, we want exactly one output coming out from it. I don't want multiple outputs coming from the same input. So I don't want to put a quarter in and get one of 3 different things. I want to know exactly what I'm going to get out of my machine if I put a quarter into it. If I put the x value of 1 in, I want to know I'm only going to get one specific y value to come back out of it. Does that make sense in terms of what we're looking to have happen and why that's a really desirable quantity if you're going to try to do mathematics? Okay. So the next thing we want to do is talk about some different ways that we can represent a function. The first way is what we've already talked about. We can represent it as a set of ordered pairs. Prior to this, the representation that you're probably the most familiar with is writing a function as an equation. something like y equals 2x plus 5. Or f of x equals 2x plus 5. You could have written it that way as well. We'll use those two notations interchangeably in this course. The third way we'll talk about is that we can write the function as a graph. And the fourth way is as a mapping diagram. When I write a graph, does everyone understand what I mean by that? Just to be clear, I mean, like something like that, where you've plotted points on the xy axis and it's forming some kind of curve. Everybody's good? That's what you were picturing when I said a graph. Maybe not that specific graph, but something on the xy axis, right? It'd be really weird if you pictured the exact graph that I just drew there. I'd be wondering what other kinds of superpowers you might have. The one that we probably don't really have any idea what I'm talking about is a mapping diagram. So let's describe or give an example of what that is. Yes? So a mapping diagram, we usually draw two kind of circles or ovals here. We usually write the circle on the left, we label that as the domain. And the circle on the right we label as the range. Actually, put those on this side. Inside of the domain, we're going to put a point and then label that point with whatever the value is of that number that's in the domain. So in this case, the domain is the numbers 1, 2, 3, and 4. And the range, similarly, would be the numbers 5, 6, 7, and 8. Everybody's okay with that idea? And then we would just draw an arrow showing how the numbers from the domain pair with the numbers in the range. So maybe 1 paired with 7, maybe 2 pairs with 5. Oh, good. Maybe 3 pairs with 5 also, and then maybe 4 pairs with 8. The question here is, how can I tell if this is a function or not? I should need to look for repeated x's, right? The x's live in the domain or the range? The domain. So if I look here, are any of these used more than once? No, because we have only one arrow originating from each of these. This is a function. Everybody's okay with that idea? Yes, sir. Yes, of course. Mm-hmm. Does everybody feel confident that you could determine whether a mapping diagram was a function or not by looking at the picture? Yes. Well, you have to really check for two things. So you have to first check to make sure that none of the x's are used more than once. And you also have to make sure all of the x's are used. So Obviously, all of them are used because they all have an arrow originating from them, and they're only used more than once. But that's kind of the easiest way to think about it. All right. What if we have a graph, and I want to determine whether a graph represents a function or not? So we'll draw a couple of graphs here. So, remind me again, what do I need to look for if I'm determining if something is a function? Repeating x's. So, if I'm looking at a graph, what does a repeating x look like on a graph? Yes. Yes, exactly. A vertical line, which is exactly what you're describing, right? So the easiest way to check if a graph is a function or not is to do what's called a vertical line test. I usually abbreviate that as VLT for vertical line test. And what this says is if you can draw any vertical line that intersects the graph more than once, then the graph is not a function. So if you can draw any vertical line that intersects the graph more than once, then that graph is not a function. So if I look at this circle here, function or not? Not. Because you could draw, say, a vertical line there, and that intersects the graph 2 times. Everybody okay with that? If I look at the next one, is that a function? Yes. No matter where I draw a vertical line, any spot I choose, that vertical line only is going to intersect the graph once. How about this last one? Not a function, right? I can draw a vertical line, say here, that intersects the graph 3 times. Does it matter that I could draw my vertical line here and it intersects it only once? Nope, because there is still a vertical line I can draw that intersects it more than 1 time. We just need that one vertical line to exist where it intersects it twice. Everybody okay with that idea? Okay. Okay. The last one we still need to talk about is what to do if we have an equation. This is the hardest situation to tell. So I'm going to try to be very narrow in what my expectation for you guys is, because This is kind of a difficult proposition. So situations that are not a function. So if you have the equation for a vertical line, like x equals 5, that's not a function. If it's just x equals and then some number, those are not functions. Circles. You should be able to recognize the equation of a circle that's not a function. You remember last year, circles we could write as x squared plus y squared equals r squared. If I give you the equation of a circle, I'd expect you to recognize that's not a function. That's it. Unless it's one of those two, I would expect you to say anything else is a function inside of this course. Now, obviously, there's going to be lots of other things that I could write that are not functions. I would not do that to you. The only situations that I'd ask you to recognize that are not functions are vertical line situations and circle situations. Okay? There are more, but that's beyond the scope of what I'd expect you guys to be able to do in this class. This feels like a good place to stop for today. I'd ask when you get home to check PowerSchool. I'm going to post an assignment on PowerSchool for you guys to work on tonight. It'll be short. You'll basically just be identifying if something is a function or not. Everybody okay with that plan?